Дорогие друзья, возможно, сейчас наступит тот самый момент.
Ladies and gentlemen, maybe this is the session that you have been waiting for a very long time. At least we will have a really an ordinary speaker, and mentioning all of his ranks and positions is going to take up the whole session. We will have the representative of a person from Bahamas, Kip Thorne. This is one of the leaders in the field of theory of probability of Einstein, and he is such a great expert that he received Nobel Prize in 2017. Author of idea and executive producer and scientific consultant of Interstellar movie. We are all tortured by questions. Is there the black side of the universe full of black holes? And can we actually see how it is born using the emissions due to the changes in the space and time? And in 1999, Kip Thorne said that 21st age will actually find the answers to these questions. And after 22 years, after this saying, here, during this forum, we'll have a great chance to find out the results of these 20 years of search. And he's going to announce it himself. I give floor to Tatiana Naumova, the head of the projects of NTV, who is going to be speaking with Kip Thorne for us. Yes, thank you very much. Actually, I'll be rather technical here because Mr. Thorne has a very interesting keynote session, and after that we will ask him questions, and I'm confident that we will actually send these questions to our little chat under the broadcast of our Open Innovations event. So, Mr. Thorne, I really hope that you can hear me. I'm actually a great fan of Interstellar. I'm really a great fan of Christopher Nolan, and it's quite obvious that I'm going to be your fan as well. So let's check how well we hear you.
You hear me now? Here I am.
Великолепно.
Do you not hear me?
Нет,
Hello, hello. Okay.
да, все отлично.
Yes, everything's perfect.
Okay, good. Shall I go ahead? So it's a great pleasure to be with you. I wish I could be with you in person in Moscow. Unfortunately, I cannot, but at least we have the technology of Zoom to enable me to join you across the airwaves. Let me share my screen with you. It'll take me a moment to get this properly set up and then share my presentation. Okay. So can you see that? Black hole, I'm going to talk about black holes, gravitational waves, and quantum non-demolition technology. So, yes?
Yes, we see greatly, and just a small reminder for those who are watching us, we have cleaned the video of you, Mr. Thorne, for us to hear you better, because you're really far from Moscow.
Okay, can you hear me okay?
Yeah, we hear you perfectly well. Please continue.
Okay, so in the 21st century, quantum technology is going to be a very big thing, a very, very big force, both for industry and for fundamental science. I think many people are familiar with quantum computing and quantum cryptography, but I want to focus on quantum metrology, high precision measurements aided by quantum techniques, and in particular on the subfield of quantum non-demolition technology, which actually historically predates everything else. We began working on quantum non-demolition technology in the 1970s, but it has been slow to come because it has been so extremely difficult, but it is here now, and it is really very exciting what it's going to do for us. So quantum non-demolition technology arose from Soviet-American collaboration during the Cold War. It's a collaboration that is driven by the challenge to create gravitational wave astronomy. The history of quantum non-demolition technology, or I call it QND for short, it's a phrase invented by my dear Russian friend, Vladimir Brzezinski. In an era of extreme international tensions, the Cold War, it was a collaboration between science of opposing nations. it illustrated, and so this illustrates the possibility of doing collaborations between scientists of opposing nations, that such collaborations can be very fruitful and can benefit all of humanity. It also illustrates the fact that new technologies often arise as byproducts of fundamental science research. Now, historically, my collaboration with my Soviet colleagues began in 1968 at a science conference in Tbilisi in the Georgian Soviet Socialist Republic, where I met Yakov Borisovich Zeldovich and Vladimir Borisovich Brzezinski. And we very quickly became close friends. And we developed collaborations with Zeldovich on astrophysics and with Brzezinski on gravitational waves. And these collaborations with Brzezinski were the fundamental research that became the foundations for QND technology. Zeldovich and Sakharov were famously regarded as fathers of the Soviet hydrogen bomb. So our collaborations were well known up to high levels of Soviet and American governments. But there seemed to be an understanding up to high levels, at least as high as the Secretary of State on the United States side, that this type of collaboration has mutual benefits. And we, my colleagues and I, lubricated the collaboration with formal cooperation agreements to help prevent lower level bureaucrats in the governments from interfering. But I want to go back in time and describe the motivations for our development of this QND technology. The history begins with Albert Einstein in 1916, who, using his newly formulated general theory of relativity, predicted gravitational waves. And Einstein's prediction said that if a gravitational wave is propagating to you through the screen and to you, then it will stretch and squeeze space perpendicular to its propagation direction, that is in the plane of the screen, stretching horizontally while it squeezes vertically, then stretching vertically while it squeezes horizontally. And the time-varying pattern of the stretch and squeeze, how it changes as time passes, could carry a lot of information about the sources of the gravitational waves. Now, it took a long time, more than 50 years, for somebody to invent a gravitational wave detector that had a real prospect for success. The person who did this was Rainer Weiss at MIT, a close friend of mine. In 1972, he said, let's take 4 mirrors hanging from overhead supports, 2 along one arm of an L-shaped configuration, the other 2 along the other arm. When a gravitational wave comes by going downward, it will stretch space along this arm, pushing these mirrors apart. We'll squeeze space along that arm, pushing those together, and then this stretch and squeeze will oscillate. Weiss said, let's use a laser beam and a technique of laser interferometry to monitor the changes in the difference of the arm lengths as the waves go by. So send a laser beam through a beam splitter, send it into this arm and trap the light between the mirrors in that arm. Trap light between the mirrors in this arm. Then when the light gradually leaks out back through the beam splitter, you will see a rising and falling intensity of the light going to the photodetector. It will rise and fall proportionally to the stretching and squeezing of space by the gravitational wave. Now, Weiss said we need to work very hard to be sure that our laser beam measures only the center of mass of the location of this mirror. It doesn't measure the vibrating atoms inside the mirror, vibrating because the mirror has finite temperature. It should average over all of these atoms in the face of the mirror, and so an average over time. So it measures only the most center of mass motion. So each mirror behaves as though it's a particle, but a quantum mechanical particle, a particle which in these gravitational wave interferometers today, a particle that weighs 40 kilograms. Imagine a 40-kilogram particle weighs nearly as much as a human being, which is obeying the laws of quantum physics and fluctuating due to quantum effects. That is what he said we needed to deal with. And Brzezinski warned us already then, at that very early time, we were going to have to worry about quantum noise in this gravity wave interferometer. He said more precisely, look, due to the laser light fluctuating will cause fluctuating light pressure noise on this mirror and on that mirror. This instrument will be sensitive only to the differences in fluctuating forces in the two arms. But that light pressure noise is one form of quantum noise caused by the quantum behavior of the light. A second form is the fluctuating arrival time of the photons, fluctuating, going in and arriving at the photodetector. We call this shot noise. And these two noises together, Brzezinski said, will enforce something called a limitation on how accurately you can measure a gravitational wave. If we increase the laser power, then the shot noise will go down because you average over more photons, down proportional to 1 over the square root of the power. The light pressure noise will go up proportional to the square root of the power. So with one going down and the other going up, there will be an optimal light pressure. And that optimal light pressure will give you a limit, the best sensitivity you can get overall. And this is now called the standard quantum limit. And for the parameters of modern gravity wave detectors, 40 kilogram particles, mirrors behaving like particles, and 4 kilometer arms, this will be 1/10,000th the diameter of the nucleus of an atom. Remember that number, 1/10,000th an atomic nucleus. That's extremely small, but important. Now, in parallel with this, my student Bill Press and I at Caltech were developing a vision for gravitational wave astronomy, what we could do with gravitational wave detectors if we could make them. And part of that vision said there are only two types of waves that can exist according to the laws of physics and can travel across the universe, bringing us information from far away. That is, two types of waves that can be used for exploring the universe. Electromagnetic waves, these are light, radio waves, X-rays, gamma rays, and so forth. And it was Galileo 400 years ago who built the first little optical telescope, pointed it at Jupiter and discovered Jupiter's 4 largest moons, and thereby created instrument-based electromagnetic astronomy. The other form of wave that can bring us information about the universe is gravitational waves, and that's all there is. And so what we wanted to do, our vision was to do with gravitational waves what Galileo did with electromagnetic waves to create gravitational wave astronomy. But when I looked at techniques for searching for gravitational waves, they didn't look very promising. And in particular, Ray Weiss's idea of a gravitational wave interferometer looked very unpromising to me at first sight. And so in a textbook, a rather famous textbook on gravitation that I wrote with John Wheeler and Charles Misner in 1973, we said that this was not very promising. And let me explain why I thought it was not very promising. I'm going to talk about what should be the magnitude of the noise in the detector if we're going to have a real possibility to detect the gravitational waves. And I had already had at that time some fairly accurate idea of how strong the strongest waves were in the universe, fairly accurate to within about a factor of 10. So if you take 1 centimeter, you divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that is being used. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000 again, you get the mirror motions, the noise level in the instruments, if you're going to have a very good chance of detecting gravitational waves, I thought at the time, and my thoughts were roughly pretty good. It turned out to be a pretty good prediction. That is only 10 times larger than this standard quantum limit. Success would mean we were quite close to this ultimate limiting sensitivity for a gravity wave detector. So this was a little worrisome. And what if I were wrong? And what if what if the waves were weaker than that? We might have to find some way to beat this standard quantum limit in order to have any success at all. So anyway, I was very skeptical of Ray Weiss's idea for a gravity wave interferometer until I had long conversations with Weiss and with my friend Brzezinski in Moscow, and I studied Weiss's 1972 technical paper on this. Gradually, I became convinced by about 1975, and I decided that I and my research group of theorists should do everything we could to help the experimenters make this a success to create gravitational wave astronomy. And so that constituted a large portion of my career from then onward until the present time. Now, so very brief history of what we did from 76 to 84. We engaged in research and development for gravitational wave interferometers. In 1984, Ray at MIT and we at Caltech created the LIGO project, Laser Interferometer Gravitational Wave Observatory project, to build this kind of a gravity wave interferometer. 1984 to 94, we made preparations for LIGO. The we was Ray Weiss at MIT, the lead experimenter there. Ron Drever, the leading experimenter at Caltech. Me as the theorist, and Robbie Vogt, who was our leader, organizational leader, the director of our first director of LIGO. And under Robbie Vogt's leadership, we submitted a proposal to the U.S. National Science Foundation, NSF, to construct facilities that would house these interferometers, and then to construct the interferometers in two steps. An initial set of interferometers, which would probably not be sensitive enough to see anything, but where we would learn what the difficulties were and where the roadblocks were, and figure out just how to build the more advanced interferometers that were required for success, and then the advanced interferometers, which would likely have success. Already by this point, we were worried all along that we might have to have QND technology to beat the standard quantum limit in order to actually have success. So we had by this time invented or conceived the basic ideas for QND technology. I'll return to that later in the talk. 1992, then our proposal to construct LIGO was approved. We got our first funding, selected the two sites for two such gravity wave interferometers in Louisiana and Washington State in the United States. 1994 to 1999, under a new director, Barry Barish, who was the real genius who organized LIGO in the end, a very large collaboration required for success, and led us through the crucial phases of this project. Under his leadership, then, we built the facilities. He created the LIGO Scientific Collaboration, a collaboration that has now grown to 1,500 scientists and engineers in 100 institutions in 20 nations. I should mention that Brzezinski's group in Moscow was one of the first two groups to collaborate with us on this. They were among the first two of all of these research groups in the LIGO collaboration. So the LIGO collaboration, then 2000 to 2010, we built and operated the initial interferometers as expected. We didn't see anything, but we learned enough to finalize the design of the advanced interferometers. 2010 to 2015, we installed these advanced interferometers and we prepared for a gravity wave search. And by now, the QND technology was getting quite mature, and we were prepared to start putting it into LIGO in 2019 or so, if it was needed, if it turned out to be needed in order to have success. But in fact, it was not needed for the first success. Let me just show you photographs. This is one of the two gravity wave detectors is seen from the air. These are the arms along which the laser beams bounce back and forth between mirrors 4 kilometers apart. These are the vacuum chambers that house that beam splitter that splits the laser beam in two and houses the corner mirrors for the two arms, one going off in this direction, the other going off in that direction. This just shows you the size of these vacuum chambers. This is a baseball player, just to get some sense of how large these vacuum chambers are. And this is one of our 40-kilometer mirrors, which behaves like a single quantum mechanical particle. It doesn't look like it's hanging freely, but it really is hanging freely, suspended by quartz fibers, for which the technology was developed at Moscow State University by Brzezinski's group. It's 14 September 2015, 3 days before LIGO's advanced detectors were scheduled to start their first search for gravity waves. A gravitational wave entered the Earth through the Antarctic Peninsula, traveled upward through the Earth. It emerged in Livingston, Louisiana at one of our two gravity wave interferometers. 7 milliseconds later, It emerged in the gravity wave interferometer in Hanford, Washington. The LIGO team, together with some scientists called the Virgo collaboration in Europe, analyzed the data for 5 months in order to be absolutely sure that what we were seeing really was a gravitational wave, and then announced the result to the world, humans' first contact with the gravitational waves. And by comparing the pattern as a function of time going horizontally, the stretching up and the squeezing downward, the pattern of the observed signal, which after being cleaned up is the gray signal, with simulations, the gravitational waves predicted by computer simulations of two black holes orbiting each other, colliding and merging. By doing that comparison, we deduced that this was, in fact, gravitational waves produced by two black holes colliding, one 29 times heavier than the sun, the other 36 times heavier, so a total of 65 solar masses. The final black hole was 62 solar masses, so 3 solar masses went off as gravitational waves. It is as though you had annihilated 3 suns and turned all of their energy into burst of gravitational waves. And those waves had to travel, according to this, the data, a distance of 1.3 billion light years in order to reach the Earth. And getting 3 solar masses of gravity wave energy off in a fraction of a second, you could deduce that the total power output during that fraction of a second was 50 times larger than the total power output from all the stars in the universe put together, an enormous power output. The computer simulations can be visual, of this source then can be visualized in this way. We are looking down from a higher dimension on the orbital plane of the black hole. Each funnel here is, it represents a black hole. So black holes look like funnels when seen from a higher dimension. The color where it is red, time is flowing much more slowly than back on Earth. And as these two black holes went around and around each other, and I'm going to bring this into slow motion, they created a veritable storm in the shape of space and the rate of flow of time. A giant splash like in an ocean, in an ocean storm on the ocean, and then an oscillation in the color coding, the rate of flow of time and the shape of space. That produced the gravitational waves that went out into the universe, bringing us information about their source. Now, by today, 2021, gravitational wave astronomy is maturing. LIGO and its partner, the Virgo gravity wave detector, have seen 100 black hole collisions. They've seen 2 collisions of neutron stars, 2 black holes being swallowed by neutron stars, 2 black holes swallowing neutron star companions, and quantum noise is becoming a problem. We're just beginning to really see what's on what kinds of phenomena are out there and get very exciting insights into black holes and neutron stars. But quantum noise, if we don't use quantum non-demolition, will kill us in the future. Here is the standard quantum limit that Brzezinski deduced. Here is, I'm plotting here the noise in the interferometer. I won't tell you the details of precisely what's being plotted up. It's a function of gravity wave frequency going from 10 hertz to 1,000 hertz on upward. The standard quantum limit is here. LIGO is almost at the standard quantum limit. We want to be here in the late 2020s as we improve our detectors. That means we have to do a very large amount of quantum non-demolition technology to go below the standard quantum limit. So the conception and development of QND technology. I explained to you how Ray Weiss invented the gravity wave interferometer back in 1972, devised techniques to make the laser beam sensitive only to the center of mass motion of the mirrors, so the mirrors behave like quantum particles. And I told you how Brzezinski predicted quantum noise and the standard quantum limit, that you have light pressure noise fluctuating, pounding on the mirrors. You have shot noise fluctuations in the arrival time of photons at the photodetector. And you increase the laser power, one of these goes up, the other goes down until there's a limiting sensitivity for the sum of the two when the power is adjusted so they're about the same. That is 1/10,000th of an atomic nucleus, and it is incredible. That is the level of noise that we we're seeing, if I go back here, that's the level of noise today. The noise level corresponds to 1/10,000th the diameter of the nucleus of an atom. Well, it was Carlton Caves, a student of mine in 1981, who realized that both the light pressure noise and the shock noise are produced by vacuum fluctuations. And let me explain what vacuum fluctuations are. If I take a box, now you remove from the interior of the box all of the electromagnetic waves that can possibly be removed, you're only left then with tiny fluctuations of electromagnetic waves, which are required by the uncertainty principle of quantum mechanics and can simply not be removed. So they're sitting there inside the box, inside any box. You try to remove everything, that's what's left. Caves realized that these vacuum fluctuations going in the dark part of the interferometers, we call it, going in the output port where normally the gravitational wave signal is coming out into the photodetector, going in backwards. They beat against the laser light to produce light pressure noise. And in addition, they go in and then come back out and beat against the laser light to produce shock noise. So both kinds of noise are produced by one thing, these vacuum fluctuations. And so Caves said, let's manipulate the vacuum fluctuation. I mean, this is incredible. You have these tiny fluctuations required by quantum mechanics. He's going to manipulate them in such a way as to prevent them from getting in the way of measuring gravity waves. And that's really an incredible idea. And it's just seemed bizarre at the time. Well, what did he mean by squeeze the vacuum fluctuations? Well, the key thing is that, let me not bring that in just yet. The vacuum fluctuations have two pieces. We call them two quadratures. One quadrature is responsible for the light pressure noise. And he wants to, and the other quadrature is responsible for the shock noise. And he says, let's squeeze the quadrature that's responsible for the shock noise. So the price that the quadrature responsible for light pressure noise goes up. And we can reduce the shock noise, increase the light pressure noise. That doesn't seem to be solving anything because one goes down, one goes up. But just hold on, just wait a minute until we see the real payoff in the end. Or we can do the opposite thing. So let me be more precise for those who understand this little bit of mathematics. This is the electric field of these vacuum fluctuations. This is the gravity wave frequency, and that's the laser frequency. So the electric field is oscillating at the laser frequency, which is a very high frequency, modulated by gravity waves or by vacuum fluctuations. L and S are these two quadratures of the amplitudes of these oscillations of the cosine omega times time, sine omega times time pieces of the electromagnetic field. Again, I'm just re-saying in more precise technical terms what I said before. There are two pieces, and one produces light pressure noise, the other produces the shock noise. So let's, and so L produces the light pressure noise, S produces the shock noise. If I make a plot of the strength of the shock noise and the strength of the light pressure noise in the ordinary vacuum, they are the same. Cave says, let's squeeze the vacuum, reducing the shock noise, or reducing this quadrature that produces shock noise at the price of increasing the quadrature that produces light pressure noise. Or we can do the opposite, reducing the light pressure noise and increasing the shock noise. Okay, so that's what we have in our hands. And now comes the payoff, though. At high gravity wave frequencies, remember this is my plot of the noise in the interferometer as a function of frequency. At high gravity wave frequencies, shock noise dominates. And so Cave says, squeeze the vacuum so that the shock noise is reduced here. At low gravity wave frequencies down in here, light pressure noise dominates. So he says, squeeze in that manner. And then in between, squeeze in this manner. And the amazing payoff, actually deduced first by our friend Bill Unruh in Canada, is that when you get in the intermediate region, these two noises partially cancel each other enough to be able to go way down below the standard quantum limit due to cancellation of the two noises, because the noises are arising from the same thing, from the arising from the vacuum fluctuations. Okay, so anyway, Caves then had this brilliant idea that this is how you would do quantum non-demolition technology, and that you could just beat the standard quantum limit by, in fact, it turns out, as much as you want if you have good enough technology. Well, so we had to then develop the technology for squeezing. Squeezing was just an idea at the time. So between 1984 and 1986, there was intense competition among experimental physicists at many different institutions to develop the technology for squeezing. It was actually Jeff Kimball who was not the first to be able to squeeze the vacuum, but he invented the best technique called parametric down conversion in nonlinear crystals. That's just a buzzword for most people. But he invented the technique that would do it using crystals in which you, not in a nonlinear manner, combine the vacuum you're trying to squeeze with laser light in order to do the squeezing. In 86 to 1990, he perfected the squeezing technology. And again, for people with some technical background, the way he perfected it was this: you send infrared laser light in to a crystal, and it interacts with itself to turn itself into green light. Then you send the vacuum and the green light in to another crystal. They interact with itself to produce a squeezed vacuum. But actually doing that required a major effort in technology development. So by 2001, the ideas were all there and the technology to do the squeezing was there. And so Brudzinski's group, my group, and Jeff Kimball then wrote a very long technical article with all the conceptual details of what must be done and describing a variety of ways that it might be done. And then the issue of importing this technology into LIGO arose. 2002 to the present, the LIGO team did it. They imported this technology into LIGO. It was a major R&D effort. And today, in 2021, the full QND technology is, as I speak, being installed into LIGO. And it will operate next year in LIGO's next gravitational wave search. In the meantime, applications of this outside of gravitational wave science are being explored, for example, in nanotechnology, applications of QND technology in nanotechnology. And major new ideas for this quantum non-demolition are being conceived and developed. So my final conclusions: QND technology and other quantum metrology technologies for very high precision measurement, will play a major role in 21st century science and industry. It's just beginning to take off. We have worked long and hard to develop these techniques, but they are going to just grow and really become better and better and better over the next decade. And this whole story is a wonderful example of new technology arising from basic science research. The challenge to create gravitational wave astronomy gave rise to QND technology, and fruitful collaborations between scientists in adversarial nations, the Soviet Union and the West, coming together to do something really great in collaboration with each other. Thank you very much. And I'll just put up here on the screen for a moment a few references. Maybe the best place to go to get started is looking at the Nobel Prize lectures by Ray Weiss, Barry Barish, and myself, which include discussion of QND technology. And then issue 3 of LIGO magazine, which you will find on the web, which is a very good place to see a non-technical discussion of bringing this technology into LIGO, the actual last step. So thank you very much.
Спасибо большое, господин Торн. У нас остается с
Thank you
вами
very
еще
much, Mr.
буквально
Thorner.
6
We
минут.
have 6 minutes to
Не
go.
успею задать все те
I
вопросы,
will not be
которые
able
прислали
to ask
для
all
вас.
the questions we
Но
received
давайте
for you,
возьмем на себя
but
смелость и
I
выберем,
will
на мой взгляд,
select
самый
the most
философский и самый
philosophical one and the most futuristic one. So let's start with philosophy. Sounds very good. I like this question. Thanks, Denise. I received this one from Denise. Hello, dear Kip. Having looked at the experience of working with Interstellar,
So what is the main driving force of humanity? Is it love or science?
I think it's neither one. I think it's curiosity. Uh, well, love may be a driving force, but I think the driving force that really makes the world better is curiosity, the desire to understand the universe, the laws that control the universe, that govern the universe, and to build technologies using great new ideas like what I have been talking about.
I agree, it is curiosity and a futuristic question. Hopefully you'll enjoy it. So, Kip, is it possible on the basis of any university today, can you open teleportation department or telepathy department? Is it possible to have it today?
Telepathy, I think no. Teleportation, yes. There is a technique, part of quantum technology called quantum teleportation. And it comes from the idea of teleportation that you see in science fiction, but it's teleporting quantum state. Now, the quantum state is the basic entity on which quantum technology is based. In quantum computing, it's basically the qubits that in which information is stored. And to be able to take the quantum state, which has information in it, and teleport it across a room or across the world or out across the universe is really a powerful thing to take that quantum state and recreate it on the other side. And in fact, it underlies the use of quantum cryptography for in banking systems for transferring money, electronic money, from one bank to another today. So quantum teleportation really is it's a quantum analog of teleportation, and it really is today part of quantum technology. And I find that quite remarkable.
So we have time for one more question for you. So maybe a long one in terms of its wording, but still, it seems to me it's about the essence. So the appearance of dark matter and energy in terms of modern cosmology, does that not mean that we go back to the old theory of ether? Or are there any discoveries in today's physics that help to answer the question, so which is the main function of our universe, why it came about, and why it was created?
So this is an amalgamation, a combination of a number of issues. An interesting question. Let me first say that the old ether, which was a major part of 19th century science, in some sense it has survived in that space and time themselves have their own properties. They are the medium, like the ether, which control the speed of light, for example, and when warped, you make black holes out of them. So there's a whole warped side of the universe that consists of objects like black holes and the Big Bang explosion of the universe that are made from warped space and time, playing roles analogous to the old ether. And so I think we do today, we have an analog of the ether, but it's very different from what the ether was. It is Einstein's conception of space and time being warped and of doing marvelous things without warping. Now, I guess there was another part to that question you have to remind me with regard to the origin of things.
Да-да-да, звучит примерно так.
Something like this, just a second. What is the main function of our universe? Are there any discoveries that would help us to approach to answering this question?
So the main function of our universe, I'm not sure. I'm not sure that the universe itself has a function, but we have a function, that is to make the universe a better place for ourselves and other beings, which we do through this kind of technology. but we also have a function that we have set for ourselves that comes out of our curiosity, and that is to understand the universe, understand where it came from, how it was born. And that, to me, is the most exciting aspect of gravitational wave astronomy, because we now have strong reason to believe that gravitational waves were created in the birth of the universe. They are so penetrating that they would travel without losing their information all the way from the birth of the universe to us today. We believe that we have strong reason to believe, based on observations and theory, that these gravitational waves were amplified when the universe was very young by a process called inflation, and that they're strong enough to be detectable in the next several decades. And so to see the gravitational waves that came from the Big Bang, from the birth of the universe, and use them to understand how the universe was born, to use them to understand the laws of physics that control the birth of the universe, so-called laws of quantum gravity, that to me is the most exciting enterprise that we, at least as scientists, have in front of us over the next several decades.
Ну и, конечно, я выхожу уже за все рамки приличия и за все
Okay,
рамки
I'm going beyond decency. Honestly, this is the last question. It's well worded. I cannot skip it. What will be the next step once you capture the gravitational wave? So what comes next?
Well, what comes next is to look at gravitation, is to use gravitational waves to revolutionize our understanding of the universe. We will see gravitational waves from many different things. We've already seen them from colliding black holes, from black holes swallowing neutron stars, colliding neutron stars. We will see them from the birth of the universe. And with all of, if you imagine, think about the huge changes in our understanding of the universe that came from electromagnetic observations since the time of Galileo, the huge revolution. We will have a similar revolution in our understanding of the universe coming from gravitational waves, and from those together with electromagnetic waves, combining the data from the two kinds of telescopes. And so I am convinced that within a century, our understanding of the universe will be radically different than it is today. And it will be as a result of these gravitational wave and electromagnetic observations. And it will be very exciting to see how these changes, what these changes are. There'll be huge surprises. And I'm eagerly awaiting those surprises and the new insights.
Господин Торн, большое спасибо вам.
Mr. Thorne, thank you so much for your keynote presentation and for answering our questions. And I have this request to make for you. Truly, when I saw Interstellar for the first time, I said one thing. I don't know if it's going to be great translation, but nonetheless. So I saw beauty. So if it would be possible to film something like that, not just for me, but all those who are fans of Interstellar, they just pray for another movie for that to come around. Thank you so much. Thank you for being with us. So I guess you have to go. So thank you so much.
Thank you very much.
Вот, Миша. Ну, а теперь давай мы потихонечку перейдем.
So little by little, let's go over to you, Mikhail. I have an honorable mission. I wanted to ask you, you've been here since what hour physically? Since 7:20 a.m. So let's give him a round of applause. Mikhail Fisher, who has been with us, so brave and strong. He's been through all the main sessions of today. Thank you so much. Tatiana Naumova, that stayed with us to talk to Kip Thorne, and everybody wanted to do it, and she got lucky. Friends, thank you so much. Noble Vision, the largest international virtual event, it comes to an end. And I would like to thank all the speakers who share their knowledge, advice, insights. Thanks to all the partners, to those who helped to make this forum so wonderful, so intense and interesting. And I would like to thank you, dear viewers. It's great that you've been with us today, and I will see you in a year. Bye-bye.